vicious when I'm spitting this vicious. I'm worse in the pit that don't listen, and you're about to get beaten by one of the best in the business. I'm ridiculous when it comes to these mathematical compositions. Street composer, I'm the rap Latin Mozart.
Hey guys, Mr. Inyard here. Today I want to talk about finding the volume and surface area of rectangular prisms and cubes, as well as figuring out what would happen if what we put inside this box is smaller than 1 cubic unit, which is what's created when you find volume. So stick around, I hope you enjoy. Okay, so let's start with volume. Volume has a formula of length times width times height. So we're actually multiplying these units by each other 3 times, which is going to create units cubed. And so the little 3 exponent means that we can call it cubed because it's literally creating a bunch of 3-dimensional cubes, which you'll see here in a moment with another video. So I got to identify my length, my width, and my height. So I like to just give them a little label so that I know the numbers I'm multiplying are 5, 2, and 4. And don't get confused, because some people want to find the length of every side, and yes, this is 5, because rules of a rectangle say opposite sides are equal, and that applies to rectangular prisms as well. But what I really want to do is just focus on length, width, and height, just one of them. So I'm going to take 5 times 2 times 4, and you get 40. Okay, and now my label, since I'm using just units here, it could be inches. Units are just a word that fills in for whatever measurement unit we're using. It could be inches, it could be feet, yards, miles, any measurement of distance. So I'm just using a U for units to be whatever it is you work with. And I'm just going to put units cubed. So I can tell this is a volume because of that little 3 exponent over the U. Now don't put the 3 over 40, because then you're cubing 40. We're cubing units because we literally did units times units times units. Okay? So that's our volume. And each thing inside of there, okay, is going to be 1 cubic unit, and we have 40 of them. Just like an area, when you did length times width and you created square units, each of those squares were 1 by 1. So let's see what happens if we take these cubic units and we were to say, instead of putting something in here that's 1 unit by 1 unit by 1 unit, what if we shipped in this box, let's say, a bunch of dice? And those dice were 1/2 inch by 1/2 inch by 1/2 inch, or 1/2 unit by 1/2 unit by 1/2 unit. What would that look like? So here I have a 1 by 1 by 1 cube. Okay, so it has a length, width, and height of 1 unit. This is a 1 cubic unit cube. All right, this is what's created whenever you find volume. A bunch of these. So in this problem, this is obviously a very zoomed in version, because they wouldn't be this big to fit in here. Okay, and you're going to see that in a video as well. But this is a zoomed in version of one of these 40 cubic units. Okay, so stick with me here. What if the dice I'm shipping in this box weren't 1 by 1 by 1? What if they were 1/2 by 1/2 by 1/2? Right? So what would really be happening is each side is cut in half. My question is, how many of these dice would I be able to fit in there, in this box, that had a volume of 40 cubic units? Let's try something. Let's cut each side in half. And we're going to say now, each of these is 1/2 unit. But remember, I have to cut each side in half, right? So this gets cut in half. And this gets cut in half. So do you see what happened when I cut each side in half? Did I just create 2 cubes out of 1? No. I actually created 8. Can you see them? 1, 2, 3, 4, 5, 6, 7, and there's got to be one back here behind this, underneath it, holding it up. So I actually created 8 cubes, 8 dice for every 1 cubic unit that's going to be in here. So what I did was the volume of a 1/2 inch or 1/2 unit would actually be 1/8, right? And 1/8 units cubed we can call. Now we have two volumes to do a math problem with. So if I'm cutting each of my cubic units into a 1/8 cubic unit, isn't that division? Isn't cutting into equal pieces division? So the problem is 40 cubic units divided by 1/8. Now, we know when we divide by fractions, what can we do? Keep, change, flip, right? We keep, we change, we flip. So that means keep 40, but we're going to write it as a fraction. Every whole number has a denominator of 1. So I'm going to write 40 over 1. Now I'm going to change division to multiplication. Okay, and I'm going to flip 1/8 to its reciprocal, fun word, 8 over 1. So obviously the denominators are just going to be 1, so this is just 40 times 8. And that'll tell me how many dice will fit. So let's recap. To find the volume, I do length times width times height, and that gives me cubic units at 1 by 1 by 1, because each of them would be perfect cubes. And I would have 40 that could fit in here. But I'm shipping dice that are smaller than 1 by 1 by 1 cubic units, and they are half by half by half. So each side, the length, the width, and the height were cut in half. By drawing the model, I was able to see that it didn't just create 2, as you might think if I cut something in half, because I'm cutting each side in half. I'm doing 3 sides in half. That's actually going to create half times half times half, 8s out of this 1 by 1 by 1 cube. So, since I'm taking my 40 cubic units and dividing them into 1/8, that's the same as 40 times 8. So that means I can fit 320 dice that are half by half by half units inside this box. So we know volume tells us the cubic units that fills a space. So again, if I work at Amazon and I'm shipping using this box, I can fit 40 cubic units of things inside. And we already found with the dice problem that if they were half-inch dice, I could fit 320 dice inside. That's going to help me maximize my profit and always use the right size box so that I'm not wasting space or money. But how do I figure out how much cardboard is needed to make this box? The cardboard would be the box cover, right? The front, the back, the right, the left, the top, and the bottom. I need enough cardboard to make this entire box all the way around. So you think of space inside of a flat object, we call that area, right? But on a solid, we have 6 different surfaces. We call them, if we're going to find out the total area of all of those surfaces, surface area. So I just wrote SA for surface area, and specifically surface area of a rectangular prism, because that's what this is. So there's a formula for that, just as there was a formula for volume. I'm going to double, or do 2 times, the length times the width. That's going to give me the bottom and the top. 2 sets of length and width. The length times the height, which is going to give me, here's the height, right? Here's the length. That's going to give me the front and the back, because I'm doing it twice. And then the width and the height, which is going to be here and here, so the right and the left. And I'm doing that twice, that's why I'm getting both sides. So that covers all 6 faces of my rectangular prism. So I can plug in my numbers, since I've labeled them already. Length and width is 5 times 2, right? That's going to be 10. Length and height is going to be 5 times 4, so that's 20. And then width and height is 2 times 4, and that's 8. So I'm going to add those together, 38. And I'm not done yet, because remember, I got this 2 out here, and that means 2 times 38. So that's going to be 76 units squared is the surface area for this box. And that's how I can figure out how much cardboard I need, or wood, whatever it is I'm using to make this box. So far, we've covered volume of rectangular prisms, length times width times height, and this works for all rectangular prisms, as well as special figures like cubes, but there's something I'm about to show you much more specific. We also talked about surface area of rectangular prisms, which is just 2 sets of length times width plus length times height plus width times height, which gives you all 6 sides, area combined. But what if we have a special figure, cubes? Cubes, like squares, are special figures. Squares have to have all 4 same sides, right? All 4 sides equal. Rectangles just have to have 4 right angles, 2 sets of parallel sides. And it's not, it can be any length, it can be any width, but cubes and squares alike have to have all sides the same. So a cube is made up of only squares, therefore every single line on a cube, all of the edges, are going to be equal. So there's shorter formulas we can use for cubes. It doesn't work if it's a rectangular prism because you're going to have different numbers. You can't use squared and cubed and things like that, exponents on numbers, unless they're the same number repeated, because exponents are repeated multiplication. And we're not repeatedly multiplying anything, we're multiplying, but they're different values for rectangular prisms. So for a cube, a couple shortcuts, you can do whatever the side is, S stands for side, cubed. And cubed, of course, is times itself 3 times. For the surface area, you could do 6 sets of the side squared, because when I do length times width, I create the area of 1, and all 6 faces of my cube will be the same. So let's just give this a number. We're going to say that if this is 5 units, every side is 5 units because it's a cube. That's what makes it a cube, the definition of it. So for the volume, I'm just going to take 5 cubed, which is 5 times 5 times 5. And 25 times 5 is 125 units. So the volume of this cube would be 125 cubic units. All right? So to find the surface area, I'm doing 6 sets of the sides squared. Well, 5 squared is 25. 25 times 6 is going to give me 150 units squared. So now you should know how to find volume and surface area of rectangular prisms, as well as understanding the shortcuts for finding the volume and surface area of a cube. Thanks for stopping by, Mr. Enyart's Mathematical Compositions. Have a great day.